Hi everyone, welcome to Trinad chemistry classes. In this video, I am going to discuss about intermediate second year chemistry topic, electrochemistry. In electrochemistry, this is my third video, part 3 of electrochemistry. In my first two videos, I have discussed about what is electrochemistry, and substances are classified into two types, conductors and insulators. Conductors are again classified into two types, metallic and electrolytic conductors. And we have seen what are the differences between metallic or electronic conductors and electrolytic conductors. Then I have discussed about what is electrolytic cell, how it works, what is its construction. Then we have seen what is electrolysis and quantitative relationship between amount of current passed and amount of reaction occurred is given by Faraday's laws of electrolysis. In that we have seen two laws of Faraday's laws of electrolysis. And in second video, we have solved some numericals based on these Faraday's laws. In this video, I am going to discuss about what is resistance, what is conductance, and based on these basic terminology in electrochemistry, I'm going to discuss about Kohlrausch law of infinite limiting molar conductivity, Kohlrausch law. In my first video, I have discussed about what is current. Then current is a flow of electrons is called current. Then we have seen substances based on the ability to allow the current through its substances are classified into two types. One is conductors and another is insulators. Conductors and insulators. Conductors means which allows the passages of current through them are called conductors. Insulators means which doesn't allow the passages of current through them are called insulators. Again, conductors are classified into two types. One is electronic conductors, or these are also called as metallic conductors. Then second one is electrolytic conductors. Here electronic means there is no chemical change. Before and after passing of electricity, there is no change in the chemical composition are called electronic conductors. Electrolytic conductors means which allow the passage of current by undergoing some chemical change are called electrolytic conductors. In this, the electrolytic conductors, the substances which act as a electrolytic conductors are called electrolytes. Electrolytes. Here we have divided in this electrochemistry topic into two parts. One is conversion of electrical energy into chemical energy, and second part is chemical energy to electrical energy. In this first part, the conversion of electric energy into chemical energy, we have started. In that, we have derived one word, electrolytic cell. Electrolytic cell is a device which converts chemical and electrical energy into chemical energy is called electrolytic cell. We have seen the construction and working principle of electrolytic cell, working principle of electrolytic cell. Then we have discussed about electrolysis. Now, let me define what is resistance. What is a resistance? Resistance is the ability of a substance, not to allow the flow of electrons, is called resistance. Resistance is the ability of a substance not to allow the flow of electrons, flow of current through it is called resistance. More the resistance, more will not be the more ability, it has more ability to not to allow the flow of electrons through it. It is denoted by letter R, capital R. It is denoted by capital R. Here the units of resistance resistance are ohms. Ohms. It is denoted by this symbol like this, ohm. If we write 2 ohm, 3 ohm means like this, they will write. This is 2 ohm or 3 ohm. This is a 3 ohm. So ohms are the units of the resistance. Units of the resistance. Now, how this resistance generally used to define means calculated by means of Ohm's law, which will be discussed in physics, second year physics. We know that V is equal to IR. So based on this triangle of Ohm's law, V is equal to IR. Then where V is the voltage, I is the current passed, V by I. Resistance is given by V by I. Now there is a one more term, that is conductance. What is a conductance? Conductance is the ease with which conductance is the ease with which a substance allows flow of electrons. Flow of electrons. See, the conductance is the ease with which a substance allows the flow of electrons. Whereas resistance is the not to allow the flow of electrons. This is called conductance. Generally, conductance is denoted by C. Conductance is denoted by C. And very simply, we can say that conductance is the reciprocal of resistance. Reciprocal of resistance, which means higher the resistance, lower the conductance. Lower the resistance, higher will be the conductance. That's why C is equal to what I can write. C is equal to 1 by R. C is equal to 1 by R. Now, what are the units of the conductance? Units of the conductance are 1 by ohms. Those are called ohm inverse, or we can write it as a mho. We can write it as a mho. Now, what are the units of the conductance? Conductance units are the ohm inverse or mhos. Ohm inverse or mhos. Now, in my first video, I have discussed the conductors are classified into two types. One is electrolytic and second one is electronic or metallic conduction. Electronic or metallic. The second one is electrolytic. Generally, the resistance of any metallic conductor, any metallic conductor is directly proportional to its length, and inversely proportional to its area of cross section. Resistance of any metallic conductor, metallic conductor or electronic. I am not discussing about electrolytic. Resistance of any metallic conductor is directly proportional to its length and inversely proportional to its area of cross section. Then what I can write? R is proportional to L, where L is the length of the metallic conductor. Or if I take some metal bar, iron bar, or something copper bar, its length. L is the length of the metallic bar or metallic substance, and inversely proportional to its area of cross section. Inversely proportional to its area of cross section. Let it be 1 and let it be 2. So from 1 and 2, what I can write? R is proportional to L by A. R is proportional to L by A. If I remove some proportionality, what I can write is R is equal to, we have to read it as a rho. This is called rho. We have to read it as a rho. We have to read it as a rho. R is equal to rho into L by A. Where this rho is called specific resistance. Rho is called specific resistance. Is called specific resistance or resistivity. Rho is called specific resistance or resistivity. Rho is called specific resistance or resistivity. Now, what I am getting? R is equal to rho into L by A. Rho into L by A. Where R is the resistance, rho is the resistivity, L is the length of the metallic conductor, A is the area of the cross section. A is the area of the cross section. Now, how to define this specific resistance? How to define the specific resistance? So now here I am defining specific resistance as when length of metallic conductor is 1 centimeter and the area of that metallic conductor is 1 centimeter square. If length is 1 centimeter, if I assume length is 1 centimeter and the area is 1 centimeter square, then what I will get? Rho is equal to, R is equal to rho into 1 by 1 centimeter by 1 centimeter. Then which means R is equal to. Now, how to define the specific resistance? Specific resistance is the resistance of a metallic conductor. Resistance of a metallic conductor whose length is 1 centimeter and area is 1 centimeter square. Whose length is 1 centimeter and area of cross section is 1 centimeter. Now, how we have defined specific resistance? Specific resistance is the resistance of a metallic conductor. Resistance of a metallic conductor whose length is 1 centimeter and area of cross section is 1 centimeter square is called the specific resistance. Specific resistance is equal to resistance when length is 1 centimeter and area of cross section is 1 centimeter square. Area of cross section is 1 centimeter square. Area of cross section is 1 centimeter square. This is, we are calling it as the specific resistance. Now, what are the units of the specific resistance? What are the units of the specific resistance? Units of the specific resistance. We know that R is equal to rho into L by A. Now, rho is equal to becomes R into A by L. We know that resistance has a units of ohms, area has a units of centimeters, length has a units of centimeters, then ohm, centimeter. These are the units of the specific resistance. These are the units of the specific resistance. So far, we have seen resistance, conductance, and then specific resistance. Resistance, conductance, and specific resistance. Now, there is one more term that is called specific conductance. Specific conductance or conductivity. So what is the specific conductance or conductivity? You see, we have seen resistance. Its reciprocal is conductance. Then we have seen specific resistance. So specific conductance, which is denoted by a Greek letter kappa. Specific conductance is denoted by Greek letter kappa. Generally, we use it to write it as a K, but we should read it as a kappa. We should read it as a kappa. The specific conductance is the reciprocal of specific resistance. Reciprocal of specific resistance. Reciprocal of specific resistance. Now, then what will happen? Kappa is equal to 1 by rho. Kappa is equal to 1 by rho. Now, what happens? What is the rho? 1 by rho is R into A by L. Then, if I rearrange the terms, 1 by R into L by A. 1 by R into L by A. Here, we know that 1 by R is nothing but C. C into L by A. C into L by A. So, this is the specific conductance. So, we know that R is equal to, so please remember, R is equal to what? R is equal to rho into L by A. From this, rho is equal to R into A by L, we calculate. We know that specific resistance is the reciprocal of specific, specific conductance is the reciprocal of specific resistance. That's why what I can write is 1 by R into A by L. If I rearrange the terms, what happens? 1 by R into this L will go to the numerator, 1 by R into L by A. There 1 by r is nothing but conductance. 1 by r is equal 1 by r. In place of 1 by r I can write it as a c. 1 by r in place of 1 by r I can write it as a c. Now what is specific conductance? Specific conductance kappa is the c into l. Now how to define this specific conductance? Specific conductance is defined as specific conductance. This kappa is defined as the, how we are defined is defined as the, it is a reciprocal of specific resistance, it's fine, but how to define it means its actual definition is when L is equal to 1 centimeter, A is equal to 1 centimeter square, when length of the metallic conductor is 1 centimeter and area of cross section is 1 centimeter square, then what will happen? K is equal to C into 1 by 1, which is equal to C. Now what is a specific conductance? Specific conductance is the conductance of a metallic conductor whose length is 1 centimeter and area of cross section is 1 centimeter square. It is the, what is it? Is the conductance of, it is the conductance of a metallic conductor whose length is 1 centimeter, whose length is 1 centimeter and the area is 1 centimeter square. Area is 1 centimeter square. Whose length is 1 centimeter and area is 1 centimeter square is called specific conductance. You see, all these terms so far we have defined based on the metallic conductors. Metallic conductors means which allows the passage of current without undergoing any chemical change. These examples for these metallic conductors are the metals. Metals are the examples for the metallic conductors. So far we have seen resistance, conductance, then specific resistance, specific conductance. Now let me discuss what are the units of this specific conductance. Units of kappa. Now just simply we have seen what are the units of the conductance. Ohm inverse, length is centimeter by centimeter square. Then ohm inverse, centimeter inverse are the units of the specific conductance or conductivity. Specific conductance or conductivity. So whatever terms we have discussed so far, 4 terms. One is resistance, conductance, specific resistance, specific conductance. All these terms are defined based on the metallic conductors. Now, generally in chemistry, we have to work with solutions. Now, how to define this specific conductance for the solution? Specific conductance for the solution. Before going to that topic, we have to know how to determine the resistance of a, metallic conductor. Resistance of a metallic conductor. How to determine the resistance of a metallic conductor? So how to determine the resistance of a experimental determination of resistance of a metallic conductor? Metallic conductor. For this, generally we use a Wheatstone bridge method. Wheatstone bridge method. In this Wheatstone bridge method, there are 4 arms will be there. We know that the resistance, if I use like these terms, this like this, then it is corresponds to resistance. It is corresponds to resistance. There are 4 resistances in Wheatstone bridge method: R1, R2, R3, and R4. In this, 2 are the known resistance. Known resistance means whose resistance is known to us. Then third one is variable resistance. Variable resistance means it is, variable resistance means its resistance can be varied. Its resistance can be varied by varying its length or area of cross section. Generally, variable resistance is to represent like this. If I write like this, this is corresponds to variable resistance. This is corresponds to variable resistance. Then the last one is unknown resistance. Last one is unknown resistance, whose resistance is needed to be determined. These 4 resistances are connected like this. Sorry. So among these, one is the variable resistance. This is R3 variable resistance. And this is R1. This is R2. Then this is the R4. This is the unknown resistance. Suppose if I want to find out the resistance of a metallic conductor, then I will connect a metallic wire. Then I will connect the 2 arms to these 2 ends. Then along this, it is connected through a galvanometer. Here, galvanometer is a device like this will be there 0, 1, 2, 3. So which is used to detect the flow of current. If there is no current is flowing, galvanometer reading is showing 0. If there is a current is flowing, then galvanometer reading will be either this side or that side. So based on the current flow, either this needle will be moved this side or this side. This is galvanometer. And then the rest 2 arms are connected through a battery. So this is the Waterston bridge method. This is the Waterston bridge method. So when current is passed through, what happens? It splits into 2 parts. It splits into 2 parts like this. Then after entering to this part, again it splits into 2 parts. Here also it splits into 2 parts. Then if we start adjusting this variable resistance, initially when we keep like this, there will be some reading at the galvanometer. So at one point of variable resistance, what will happen? The reading in the galvanometer becomes 0. That is, there is no net current flowing through the galvanometer, because here the whatever is entering and opposing currents are same. That's why there is no net reading 0 in this galvanometer. At this stage, we can say that bridge is balanced. Bridge is balanced under these conditions. R1 by R2 is equal to R3 by R4. So from this, we can determine the variable resistance. We can determine the variable resistance R4. R3 by R2 by R3 into R1. R2 by R4 is equal to R2 into R3 by R1. From this, we can determine the variable resistance. We can determine the variable resistance. So by using this Waterston bridge method, it is possible to determine the resistance of an unknown metallic conductor. Now, here the problem is how to determine the conductance of a solution. Once, if we get the resistance by using those formulas, whatever formulas we have discussed, by using those formulas, we can determine the conductance and specific conductance. But how to determine the conductance of a solution? Because in chemistry, we may need to handle with the solutions. We may need to know the resistance or conductance of a particular solution. How to determine it? So for this, there is a device that is called conductivity cell. This is called conductivity cell. This is specially designed for determining the conductance of a solution. So conductivity cell, any conductivity cell consists of 2 metallic wires, platinum wires. In this, 2 platinum foils are placed, and the distance between the platinum foils is these platinum foils is 1 centimeter, and area of cross section between these 2 platinum foils is 1 centimeter square. So its length is 1 centimeter, and its area of cross section between these 2 platinum foils is 1 centimeter square. And this is fitted to like this, and it is kept in a like glass foil like this. Then in order to avoid any disturbance in these lengths, so what it is connected to this glass. So it is fixed. So this is the one basic, any electrolyte, any conductivity cell if you take. So this is the design of the conductivity cell. Then what they will do, they will connect to the. So suppose if I want to find the resistance of a solution, now what I will do is I will insert conductivity cell like this. I will insert conductivity cell like this. Conductivity cell in the solution. Conductivity cell in the solution. Then there are two arms. The two arms are connected to the Wheatstone bridge like this. So here this is R1, R2, this is the variable resistance. Then in place of R4, I will connect to the fourth arm of a Wheatstone bridge. Fourth arm of a Wheatstone bridge. This is the battery. So in this way, we use it to determine the conductivity of a solution. Conductivity of a specific conductance of a solution. Here, this is the way to determine the conductance of a solution. Conductance of a solution. You see here, there are various designs for this conductivity cell. For any conductivity cell, L and A are constants. That's why this L by A is called cell constant. This L by A is called cell constant, and it has a units of centimeter inverse. It has a units of centimeter inverse. It has units of centimeter inverse. Now let me define specific conductance of a solution. Specific conductance of a solution is the conductance of it. Specific conductance of a solution is the specific conductance of a solution is the conductance of a solution which is placed between the platinum foils of 1 centimeter length apart, and the area of cross section is 1 centimeter square. 1 centimeter square. Specific conductance of a solution is the conductance of a solution which is placed between the platinum foils of 1 centimeter length apart, and area of cross section is 1 centimeter square. So very simply, if the solution which is placed between the platinum foils which are separated by 1 centimeter, and its area of cross section is how much? 1 centimeter square. So if length is 1 centimeter and area is 1 centimeter square, length into area gives the volume. Length into area gives the volume. So here length into area, volume is the length into area, 1 centimeter into 1 centimeter square. This is corresponds to 1 centimeter cube. Now, simple way of defining the specific conductance of a solution is the specific conductance of a solution is the conductance of 1 centimeter cube of solution. 1 centimeter cube of solution. Specific conductance of a solution is the conductance of 1 centimeter cube of solution. Specific conductance of a solution is the specific conductance of a solution is the conductance of 1 centimeter cube of solution. 1 centimeter cube of solution. Now let me discuss one more term, that is molar conductance. Molar conductance, which is denoted by lambda, or I can this lambda. I will use it to denote with lambda or this lambda. Here molar conductance is the conductance of VCC of solution. VCC of solution. CC means centimeter cube, containing 1 mole of electrolyte. 1 mole of electrolyte, which is placed between platinum electrodes, platinum foils of 1 centimeter apart, and area is VCC. Area is VCC. You see, when the VCC of solution is placed between the platinum foils of 1 centimeter apart, and area of cross section is how much? VCC. You see, here molar conductance is the conductance of VCC of solution containing 1 mole of electrolyte, which is placed between platinum foils of 1 centimeter apart, and area of cross section is 1 centimeter square. Area of cross section is 1 centimeter square. 1 mole of, here, what is the difference between specific conductance and molar conductance? Molar conductance is defined for 1 mole of electrolyte containing VCC of solution. So there is no specification in the volume, but here the electrolyte should be present in 1 mole. 1 mole of electrolyte present in VCC of solution. Then whatever conductance we are getting, that is molar conductance. If whatever may be the amount of substance, if it is 1 cc of solution, then it is called molar conductance. Molar conductance. Thank you for watching Trinath chemistry classes. Please subscribe, like the video, and share. Thank you.